Usually when we talk about a computer upgrade, there is this comforting expectation of just simple linear progress.
Right, like buying a slightly faster car.
Exactly. You get a new smartphone, the apps open a fraction of a second quicker, the battery lasts maybe an hour longer, and you just sort of accept that the microchips inside got a tiny bit smaller.
Yeah, it's clean, it's predictable.
We like our technological progress to be visible, measurable in terms we already intuitively understand. But if you step into the world of what is happening right now in quantum computing, that predictable upgrade cycle is completely shattered.
Oh, absolutely.
We aren't looking at a slightly faster car anymore. We are looking at a machine that might literally be pulling computing power from parallel universes.
I mean, it is the absolute definition of a paradigm shift. And frankly, it's happening much faster than almost anyone in the scientific community anticipated, even like 5 years ago.
Welcome to today's deep dive. Today is June 4th, 2026, and if you haven't been paying microscopic attention to the tech world over the last few months, you might have missed that we are collectively standing on the edge of a cliff.
A very steep cliff.
Right. Back-to-back breakthroughs from Google and Microsoft have violently accelerated the timeline for a working, scalable quantum computer. Our mission today is to unpack a massive stack of recent reports, tech keynotes, and physics analyses to understand this sudden, terrifying, and awe-inspiring acceleration.
Because this isn't just about faster gadgets for your desk.
No, not at all. This is about machines doing calculations so vast they threaten the entire foundation of our digital privacy and maybe even challenge our foundational understanding of reality itself.
Which is a lot to take in.
It is. So I'll be your curious guide through these sources, trying to wrap my head around the impossible, while my co-host here will be the voice of reason, helping us connect the dots on what this actually means for your everyday life. Okay, let's unpack this.
Let's do it.
Let's start with the sheer scale of the mathematical shockwave Google recently set off. I was reading through the specs on their new Willow chip, and the numbers frankly just broke my brain. Walk us through what they actually achieved here.
So to understand the gravity of the situation, you really have to look at the benchmark test Google ran on this 105 qubit quantum processor.
Okay.
They gave the Willow chip a highly complex mathematical problem, and it completed the calculation in under 5 minutes.
5 minutes. Seems fast, but, computers are fast.
Right, but if you were to feed that exact same problem into the fastest classical supercomputer on Earth today, it wouldn't take days or even centuries.
How long?
It would take 10 septillion years to solve.
See, that is a number so incredibly huge that it just loses all meaning. Like, it sounds made up.
It really does. To give it some context from the sources, 10 septillion years is roughly 720 quadrillion times the age of the entire observable universe.
Oh my God.
Yeah. So we are comparing 5 minutes of quantum processing to literally billions of lifetimes of the universe using classical processing.
That immediately demands an explanation of how this is physically possible. We constantly hear the buzzwords, superposition, qubits, and usually someone brings up the analogy of a mouse in a maze trying every path at once.
Right, the classic maze analogy.
Yeah, but for an audience that follows tech, that feels a bit elementary. What is actually happening under the hood that allows a machine to bypass the age of the universe?
Well, let's elevate the analogy. Imagine a classical computer trying to find a specific phrase hidden in a massive library.
Okay.
It has to pull one book off the shelf, read it cover to cover, put it back, and pull the next one. It does this incredibly fast, but it is fundamentally sequential, one at a time.
Right.
A quantum computer, utilizing superposition, is more like turning off all the lights in that library and shining a highly specialized flashlight that illuminates every single page in the building simultaneously.
Wow.
But it doesn't stop there. It uses a property called interference.
I always get tripped up on interference. How does it isolate the correct answer out of all that noise? I mean, every page at once sounds like chaos.
Think of it like noise-canceling headphones.
Okay.
Those headphones detect the sound wave of an airplane engine, and they generate an inverted sound wave. When the two waves meet, they cancel each other out, leaving silent.
Right. Destructive interference.
Exactly. Inside a quantum computer, the algorithm is designed so that the probability waves of all the incorrect answers destructively interfere with each other. They cancel each other out.
Oh, that makes sense.
Meanwhile, the probability waves of the correct answer constructively interfere. They amplify each other. So when you finally measure the system, the only thing left standing is the correct answer.
What's fascinating here is how that exact mechanism, superposition and interference, bridges directly into some of the most profound debates in theoretical physics.
It definitely does.
The sources heavily reference the many worlds interpretation of quantum mechanics, championed by physicist David Deutsch. This is where the story gets incredibly spooky.
It absolutely does. To understand why serious physicists like Deutsch look at these computers and see parallel universes, the sources point back to the famous double-slit experiment.
Right, the classic physics experiment.
Yeah. If you fire a single particle of light, a photon, at a barrier with two tiny slits, common sense dictates it must go through one slit or the other, like a bullet hitting a wall.
But it doesn't behave like a bullet.
No.
Over time, as you fire those single photons one by one, they build up an interference pattern on the wall behind the barrier. They leave a pattern that looks exactly like a physical wave crashing through both slits simultaneously and interfering with itself.
Which is mind-boggling.
But you are firing them one at a time. What could it possibly be interfering with?
That is the multi-trillion-dollar question. If you add more possible paths, certain bright spots on the wall become dark. Something invisible is actively shaping the outcome.
And Deutsch's theory.
David Deutsch's interpretation is that when we witness this interference, we are actually watching our particle interact with counterpart versions of itself in other branches of reality.
Right, like actual other universes?
Not ghosts, but real, physical, mathematical shadow versions of the photon moving through the other possible paths in parallel universes.
Taking that philosophy back to Google's Willow chip, I mean, the implications are staggering. If a machine sitting on a desk in our universe is solving a math problem that would technically require more memory than there are atoms in the observable universe, where is the actual computation taking place?
It's a great question.
The math strongly suggests the quantum computer isn't just running fast, it is physically distributing the calculation across multiple unseen branches of reality.
It is using the multiverse as a hidden computational engine.
Which is just wild to think about.
Right. And whether you view that as just incredibly complex probability math or literal parallel universes, the functional result is the exact same. The machine is tapping into a layer of reality that classical physics simply cannot explain.
Okay, so Google has emphatically proved the math is possible, but let's be pragmatic for a second. It is really fun to talk about tapping into the multiverse, but in the real world, these quantum states are incredibly fragile.
Extremely fragile.
The sources talk constantly about the problem of noise. Ambient heat, tiny physical vibrations, even a random cosmic ray passing through the atmosphere can cause the system to instantly lose its quantum state.
It's called decoherence.
Right, decoherence. So if Google proves the math works, how do we physically keep the machine alive long enough to actually finish a calculation without the universe destroying it?
That fragility has been the great bottleneck of the last decade. And if they couldn't solve it, quantum computing would forever remain a neat laboratory parlor trick.
Which brings us to Microsoft.
Exactly. This brings us to the second massive breakthrough in the sources, announced by Microsoft at their Build 2026 conference. They unveiled the Majorana 2 chip, which moves away from traditional designs and uses a completely different architecture called topological qubits.
I saw the phrase topological qubits everywhere in the Microsoft keynote, but they kind of glossed over what it actually means.
Think of a traditional qubit, like a perfectly balanced coin spinning on a table. The slightest bump of the table, the slightest breeze, and the coin falls over. The data is destroyed.
Very fragile.
Right. A topological qubit, on the other hand, stores information in the structural geometry of the system. Imagine tying a physical knot in a shoelace.
Okay, a knot.
You can shake that shoelace, heat it up, blow a fan on it, but the knot remains structurally intact. Topological qubits encode the data in a way that makes it fundamentally immune to small environmental disruptions.
That's brilliant. So by storing the data in the knot rather than the spin, they can ignore the noise. What kind of time improvement did this actually buy them?
Historically, a qubit lifespan was measured in microseconds.
So practically nothing.
Literally 1/1,000,000th of a second before the data vanished into noise. Microsoft's new topological chip held a quantum state for 20 seconds.
Wow.
And in highly controlled conditions, up to a full minute.
Wait, full seconds? Not milliseconds.
Full seconds.
That sounds like a completely different universe of computing. Going from a millionth of a second to a full minute isn't an upgrade. It's a completely new reality. How did they jump that fast?
What is truly revolutionary here is the method of discovery. It wasn't just human ingenuity sitting in a lab running trial and error.
No.
Microsoft utilized an AI agent system called Microsoft Discovery to analyze nearly 20 years of scattered, fragmented research data across the entire globe.
This detail reads like a science fiction thriller. The AI didn't just summarize academic papers. The sources note that the AI sifted through 2 decades of raw telemetry and found a single improperly calibrated temperature sensor from an old experiment years ago.
Yes, a microscopic hardware mistake that human scientists had completely missed.
And that mistake had been quietly skewing the foundational data of the entire industry and sending everyone down the wrong development paths.
It perfectly illustrates the new paradigm we are entering. AI is now doing the unglamorous, painstaking work of cleaning up messy physical data and spotting microscopic human errors that derail progress. And it led to a massive physical change in the hardware, too.
Right. The AI helped them realize they needed to switch the superconductor material shielding the qubits. They went from using aluminum to using lead.
The exact same heavy metal they drape over you at the dentist's office to block X-rays.
Yeah, they used it to shield these tiny qubits, which are barely 1/100th of a millimeter across, from ambient cosmic rays.
But wait, I have to play devil's advocate here. Wait, tech companies promise the moon all the time to pump up their stock prices.
They do.
Microsoft is now projecting a fully commercial, scalable quantum machine by 2029. Can we really trust this target, or is this just marketing hype?
It is a crucial question, and you should always maintain a healthy skepticism. A claim of a massive exponential improvement is just a marketing line until it is independently reproduced outside of Microsoft's internal labs.
The gap between a controlled lab demonstration and a working commercial machine has historically tripped up everyone in this field. However, the theoretical foundation is solid. And if that 2029 timeline is even reasonably accurate, it triggers a terrifying countdown for our entire global infrastructure.
Because if they really can keep these qubits stable for a full minute, we aren't talking about lab tricks anymore. We are talking about enough time to run sustained, incredibly complex algorithms.
Which directly threatens the encryption holding the modern world together.
Right. This introduces the concept of Q-Day, the hypothetical day a quantum computer goes online and breaks modern cybersecurity. Walk us through how our digital lives are actually protected right now and why this machine threatens it.
So, nearly every bank, government communication, and secure internet connection relies on an encryption standard called RSA 2048.
Okay.
It is built on a very simple mathematical one-way street. Think of it like mixing paint. If I give you a bucket of yellow paint and a bucket of blue paint, it is incredibly easy to mix them together to create green. But if I hand you a bucket of green paint and ask you to chemically unmix it back into the exact original shades of yellow and blue, it is practically impossible.
That makes sense.
In mathematics, RSA uses prime numbers. Multiplying two massive prime numbers together is easy. Finding the original primes from the resulting massive number is the hard part.
And doing that reverse engineering is so computationally heavy that classical computers essentially choke on it.
The sources note that if every supercomputer on Earth worked together to break one single encrypted message, it would take about 1 trillion years.
Precisely. That trillion-year mathematical wall is the security guarantee protecting your bank account right now.
But
back in 1994, a mathematician named Peter Shor created an algorithm specifically designed for a quantum computer.
Shor's algorithm.
Shor's algorithm doesn't test possibilities sequentially. It acts like a highly sophisticated chemical solvent that perfectly unmixes the paint. It uses the quantum interference we discussed earlier to amplify the periodicity of the numbers, fading out the incorrect factors and illuminating the correct ones. And how fast are we talking?
A stable quantum computer running Shor's algorithm wouldn't take 1 trillion years. It would take hours, maybe minutes.
So what does this all mean? The most chilling part of the source material for me isn't just the future threat. It is the concept of harvest now, decrypt later.
Yes, that is a huge concern.
We tend to think Q-Day is a 2029 problem. But bad actors, state intelligence agencies, massive cyber syndicates are already vacuuming up encrypted data today.
They are hoarding dormant cryptocurrency wallets, highly classified private messages, health records, corporate trade secrets.
And they can't read any of it right now. But they are just patiently storing it on massive server farms, waiting for the day a machine boots up and turns the lock.
If we connect this to the bigger picture, the geopolitical and structural fallout is staggering. The U.S. agency NIST, the National Institute of Standards and Technology, is targeting 2035 to establish comprehensive post-quantum encryption standards.
2035. That's a long way off.
And transitioning the entire globe to new cryptography is being called the largest infrastructure project in the history of the internet. And it is not going to be a clean overnight software update.
Because it won't happen everywhere at once. The sources detail a coming splintering of the internet. Right now, the global internet feels completely seamless.
Right.
If you buy something online, your laptop in Sao Paulo talks to Amazon, which talks to MasterCard, which verifies with a server in Hong Kong. It happens in 2 seconds because every single system speaks the exact same RSA cryptographic language.
But in a post-quantum transition, that seamless web is going to fragment into heavily guarded tiers. Major banks, military networks, and wealthy nations will migrate to quantum-safe networks first.
Leaving everyone else behind.
Exactly. Developing economies, municipal power grids, and legacy software systems will lag decades behind. If even one single link in that global transaction chain hasn't updated its cryptography, the secure connection breaks down.
That sounds like a nightmare.
The internet we've known for 30 years, a single, unified global standard will effectively die, replaced by a walled garden network, where anything outside the safe zones is treated as a compromised wasteland.
Okay, if you are listening to this and feeling a sense of impending doom about the death of the internet and the compromise of all your private data, I get it.
It's heavy stuff.
But we have to step back and ask why. Why are companies like Google, Microsoft, and IBM pouring tens of billions of dollars into this? Why is China investing a reported $15 billion into quantum research facilities? If breaking encryption is this dangerous, what is the spectacular upside of breaking binary computing?
The upside is that classical computing is hitting the absolute physical limits of what is functionally possible in our universe.
Moore's law, right.
You've likely heard of it, yeah. The idea that computing power doubles every few years because we figure out how to shrink transistors. Yeah. But we have shrunk them so much that they are now only a few atoms wide.
That's incredibly tiny.
At that atomic scale, electrons stop acting like predictable electrical signals and start quantum tunneling right through the physical barriers. The binary system of ones and zeros is literally breaking down. But far more importantly, classical computers simply cannot simulate nature.
This is the part of the research that gets incredibly hopeful. Let's look at the field of medicine. The sources point out that classical AI, like Google's AlphaFold, did an unbelievable job predicting the physical shapes of protein structures.
It did.
But it hit a hard wall when it came to molecular interaction.
Exactly. Finding the physical shape of a protein is fundamentally a geometry problem. But how molecules actually bind to each other, how a drug interacts with a specific target cell in your body, that is purely driven by quantum mechanics.
Right.
It is about how complex electron clouds overlap and share energy. Classical computers can't process those electron clouds. They have to rely on rough approximations. That is why drug discovery today, even with AI, is still mostly a wildly expensive game of trial and error in a wet lab.
But with a sufficiently powerful quantum computer, we aren't approximating anymore. We can perfectly simulate those exact quantum mechanical interactions in a digital space.
We could design drugs flawlessly tailored to a specific disease on a molecular level before ever synthesizing a physical pill.
Effectively ending the era of trial and error in big pharma, and it extends far beyond human medicine. The sources give this incredible example of a nitrogen-fixing bacterial enzyme.
Oh, this is one of the holy grails of chemistry. There is a naturally occurring enzyme in certain bacteria that effortlessly pulls nitrogen straight from the atmosphere at room temperature.
Which is amazing.
If humanity could replicate how it does that, we could create room temperature agricultural fertilizer. It would revolutionize global food production and massively reduce the staggering amount of energy we currently burn creating synthetic fertilizers.
But right now, we can't digitally model it because tracking the complex interactions of all those electron clouds is simply too vast for a classical supercomputer. A quantum computer could simulate it flawlessly. And then you look at the realm of optimization. Institutions like Goldman Sachs and JP Morgan aren't just interested in tech hardware. They're preparing to use quantum systems to perfectly allocate capital without the blind spots of classical models.
And logistics empires want to use it to route global supply chains dynamically, instantly factoring in weather, fuel costs, and labor in real time.
Right now, we rely on classical approximations that cost the global economy untold billions in wasted resources and emissions.
Quantum computing offers the promise of a civilization that operates close to its mathematical limits of efficiency.
The way I've come to think about it is this. We've spent all of human history walking around the Earth, picking up materials, wood, iron, lithium, and asking, okay, what can I build with this?
Like scavengers?
Yeah, we are entirely constrained by the properties of what we happen to find. Quantum computing flips that paradigm on its head. It lets us start with the complex problem and then mathematically design the exact perfect material to solve it from scratch. We graduate from being scavengers to becoming true architects of physical matter.
It is a profound philosophical shift. But as we look at this horizon, it's crucial to acknowledge the sobering reality of how this post-digital age will practically unfold. It's going to create a new, unprecedented digital divide across the human race.
Right, because no matter how fast this moves, I'm not going to have a quantum laptop sitting on my kitchen table anytime soon.
Precisely.
Yeah.
The smartphone revolution democratized technology. It miraculously put a networked supercomputer in the pockets of half the planet. Quantum hardware is fundamentally different.
Because of the cooling, right?
Yes,
Yeah.
because these topological chips are so incredibly sensitive to ambient noise, they require massive warehouse-sized cooling systems that drop the temperature to near absolute zero, literally colder than the vacuum of deep space.
Incredible.
Because of those extreme physical constraints, direct access to these machines will be heavily guarded and restricted to a few dozen global institutions, sovereign governments, and massive corporations.
So the most powerful tool humanity has ever built, the multiverse engine that can cure diseases and perfectly allocate resources, will be locked behind a few highly secure walls.
Unfortunately, yes.
And the rest of us, billions of regular people, smaller businesses, entire developing nations, will only be able to interact with it through a handful of megacorporations who dictate the terms of access. It begs a massive question about who ultimately gets to shape this new civilization.
It absolutely does.
Here's where it gets really interesting. As we wrap up this deep dive, I want to leave you with a final thought to mull over, one that builds on the fundamental strangeness we discussed at the beginning.
Okay.
We started by talking about the murky, mind-bending reality of quantum physics, how these machines are using superposition and interference to navigate a web of probabilities, maybe even reaching into a multiverse to pull out answers.
Right.
If human civilization is truly about to transition from living in a rigid, predictable, classical world to one where we harness the hidden probabilities of the universe to bend biology, chemistry, and data to our will, what does that make us?
It forces us to hold a mirror up to our own biology and our own minds.
I think about human intuition. I think about consciousness itself. We don't operate like binary computers, testing one logical path at a time.
We definitely don't.
We comfortably hold contradictory thoughts in our heads. We navigate incredibly complex social and physical probabilities instantly, arriving at answers without knowing exactly how we calculated them. Are our own brains, in some deeply mysterious way, just a biological version of a quantum computer?
That is a profound thought.
If the universe fundamentally operates as a vast, vibrating web of probability and interference, maybe we aren't just building a dangerous new machine. Maybe, for the very first time in human history, we are finally learning to build a machine that speaks the universe's native language.
And we are only just beginning to learn our first few words.
Thank you for joining us on this deep dive into the quantum frontier. Keep questioning the reality around you, and we'll see you next time.